Opposite patches of the sky, never touching, share almost identical temperatures. This surprising fact is the horizon problem, and inflation explains it. In short, distant regions look identical, which is puzzling. A faint microwave glow fills the sky, and it is everywhere. It records the universe when it was about 300,000 years old. Surprisingly, its temperature varies by only a few parts in 100,000. That uniformity creates a real puzzle about causal contact across space. For instance, opposite sky patches share the same 2.7 Kelvin value to high precision. Net result, the cosmic microwave background looks extraordinarily uniform across distant regions. Light had only so much time to travel since the Big Bang. That limit creates a horizon around every observer in space. Regions separated farther than twice that horizon never exchanged signals. So opposite patches we see could never have equalized their temperatures. This is the horizon problem stated in causal terms, and it is simple to grasp. Therefore, uniformity cannot follow from ordinary light travel alone. Thermal equilibrium needs particles to collide and exchange energy. But distant regions lacked that communication before the CMB formed. That removes the usual explanation for matching temperatures across space. So we must seek a new mechanism that acted earlier and much faster. For example, if regions were once in contact, they could thermalize and later drift apart. Thus the core issue is causal contact at very early times. Cosmic inflation proposes a brief burst of accelerated expansion. It happened within the universe's first tiny fraction of a second. The stake is huge because inflation rewrites early causal structure. Mechanically, inflation stretches space so small regions become vast. Those regions start in thermal contact before inflation blows them apart. Bottom line, inflation makes causal contact possible for distant regions. Inflation grows distances exponentially, roughly by e to the n factor. Even a small n of about 60 makes enormous separation possible. That means regions that once touched become far apart very quickly. As a result, the entire observable universe can share a common past. If 1 centimeter expanded by e to the 60th, it becomes astronomical in size. So inflation converts tiny uniform patches into our huge sky. Inflation predicts tiny quantum fluctuations that stretch into cosmic ripples. Those ripples seed galaxies and imprint patterns on the CMB. We observe the predicted, almost scale-invariant fluctuation spectrum today. That match is strong, but not the only support for inflation. For instance, temperature anisotropies match inflationary models at percent levels. In short, observed CMB patterns favor an inflationary origin. Alternatives like bouncing or ekpyrotic models exist, and they try different physics. None yet match inflation's explanatory power and observational fit fully. Open questions remain about what triggered inflation and how it ended. Detecting primordial gravitational waves would be a decisive clue. Projects like BICEP and future satellites aim to find that signal. So while inflation fits, the cosmic story still holds mysteries. Remember, distant sky patches matched temperatures because inflation gives them common history. If this surprised you, subscribe for more calm, visual deep dives into cosmology.